Our final session of the 2022 IBC edition of the ST2110 Launchpad is going to be presented by Hartmut Opfermann, who is a Senior Solutions Architect for Qvest. And the idea here is we want to not only talk about what a network should do, but how you do networks and how you fix them when they're going bad. So I think this is a really important way to wrap up our session here. And take it away, Hartmut.
Thanks very much, Wes. Yeah, this is about installation and troubleshooting. So putting all the things we have heard in theory now together into a system that that really works. And of course, as Qvest, we are a system integrator. We have built a lot of systems. Now you hear a condensed version of everything that we encountered on the numerous systems we built. Of course, it should not give you the impression that so many things do go wrong in every project, but it's just, yeah, now it's very condensed. Okay, I'll start with a little to set up the scene, just with a little SDI analogy, because that's something we know and we can refer to. IT engineers like to think of things in layered structures, and so I'll compare again a little bit the SDI world to what the layered structure looks like in an IP environment. And then I'll go through the different layers and look what to look out for, what they are about, and yeah, how to fix things or how to find things if something's not going wrong, not going well. So in the traditional world, we had this SDI router, which was pretty much a black or a green box, or however, and you had your input and output signals. And a couple of years ago, when we first talked about these systems, there were presentations where in a system, just the SDI router disappeared, and then a network switch was put into place. And it seemed like nothing else had to change. That's a little bit not the right perception, because actually the network switch does not directly replace the SDI router. But you have to look a little bit into the SDI router, what's in there. I mean, if you have a large modular SDI router, you can see it like physically that you have different cards. You have an input stage where things get into the router. You have an output stage where things come out. You have a crossbar that connects input to outputs. And you have a controller, which controls everything that goes on inside the SDI router. And what we're doing in the IP systems, we're taking this apart, and with that, we create much more flexibility, because you don't have to have your input and output stage in the same box, but you can move them around. And the network is just the crossbar. And you can have your senders and receivers being just gateways, so that you have your traditional SDI inputs and outputs, but you can also put them back into the devices so that you get rid of the SDI connection, and still you can move them all around your facility and connect them to the same network. So that's where the network comes into play. It's the central core, the central crossbar of your distributed stream video and audio and data stream router. So let's get to this layered stack. And I said network engineers like to talk about things in layers because that's a good way to structure things and to get complexities under control. But also in the traditional SDI world, I mean, we're not so many layers, but you could think of it as layers, where you have your SDI router or equipment in the middle, and you have a physical layer because you needed cables anywhere, and something could go wrong with the cables. And also you usually had some kind of control structure on top of it. And we just have a few more layers, and that helps in troubleshooting because you have a more layers where you can interact with the system and find where things go wrong and fix them yourself instead of having to rely on your SDI router vendor fixing them for you if something goes wrong there. So we have those 5 layers: the physical layer, the network and PTP layer. Then we have a layer of network control, a layer of stream control, and a layer of broadcast control. Physical and broadcast control we had previously as well. And with these layers, they each have their specific function, but they're not necessarily, every layer is an individual system. So depending on what systems you are using, which vendors, some might combine broadcast control and stream control into one product. And so they perform the tasks of those 2 layers in one product. Others may combine stream control and network control into one layer. And yeah, you just have to see how this needs to be laid out in your design. Some designs, if you have like a monolithic architecture where you just have a single switch because it's a small facility, or you have a big switch, then you might not need a special network control layer, but you still need the stream control layer. So it's a tool. This layered structure is a tool to see how your network is designed compared to this model. And this not only helps you in design, but also installation. So you can structure your installation and the buildup of your system based on those layers, because each layer is a foundation for the layer above it. So you should make sure that you first install the lower layers and make sure that they work correctly, and then build the others on top of it. So of course you do your physical installation and make sure that every links are there and there is no broken cables or mismatched fibers or whatever. And then you build the network on top of it and the PTP structure. And then you make sure that your network, that your routing protocols are working fine. And if that's okay, then you build the network control layer on top of it, if you have one. Yeah, and with the troubleshooting, it's similar. You can either start at the bottom if you want, or you can use a divide and conquer methodology where you start at the middle, and if at the middle everything looks all right, then you know that everything in the below it is okay, because the foundation needs to be there, and then you can speed up your troubleshooting methodology because you do not have to go through all the layers. So let's go through the individual layers. We all know the physical layer. It's about cables. It's about SFPs, especially with network devices. You have a lot of optical interfaces, and to be sure to have the right adaptation for the type of fibers you're using, it's good to have this, or to look at this physical layer. Of course, what we look out for is the cable correctly connected. That seems to be obvious, but there are some specific things in those high bandwidth IP connections, especially concerning fiber polarity and plug type. We have multiple fiber optic fiber optic connectors, or the MPO connectors. And of course, you want to look for a FEC type, because these high bandwidth connections, they come with a forward error correction, and there's quite some different times. Usually it works out quite well and is plug and play, but if it isn't, then that's something you may have to look at. The tools to look at those things is a switch user interface. I usually look at the command line interface, and I encourage you to not be afraid of the command line interfaces. Some people seem to be. I find them quite useful because they're very simple user interface and easily can be easily scripted, or you can build yourself a library of different things you can do on the command line. So even if you don't know the command line by heart because you use it every day, you can have like a book of snippets that you can use just to do certain tasks, which can be quite handy even for those who do not work on a day-to-day basis on a switch. One part, but if you don't want to use the command line, most switches also have some kind of web interface, or you have a network management system where you can also find these things. One of the, especially for the physical layer, is the digital optical monitoring statistics. Those help you identifying, is there at least light coming through, even if it's a mismatch in speed or whatever. Yeah, then you can see this. To dig a little bit deeper, I talked about connectors. This is the MPO connectors that you have with some of the 100 gig and 400 gig connections, where there are multiple fibers. This type of connector is up to 12 fibers. There's also some for 24 fibers. In a standard 100 gig connections, if you use those connectors, typically 8 fibers are used. And these come in as most connectors, and I hope you can see it here on the picture. These come in a female and a male variant, but they are only slightly different with these 2 pins there. And it's actually possible, unlike other connectors we know, to plug a female connector into a female receptacle. And so this does physically work, but it does not optically really work very well. If you're lucky, it doesn't work at all, because then you're immediately suspecting something. If you're unlucky, then it does work halfway, and then you think it works, but later discover, no, it doesn't. So that's something to look out for in the installation. Usually installation is, I mean, that's the thing we have under control, but that's a thing a colleague of mine stumbled in one of the projects. You also have, you can break out these multiple fiber connectors into multiple LC connectors, so that you can break out 400 gig, for example, into 425 gigs, and then but there you need to also watch out for the polarity of the fibers, as we know. That's the DOM statistics. Here you can see that on the command line, but as I said, you can also see this on a graphical user interface, depending on your switch model. You get especially the receive power of the SFP, so that you know light is coming through. This works even if the switch cannot make a connection because the FEC is not correct, or the speed, or something else. You see that there's light coming through, and then you know your cables are at least correctly polarized. And on the other hand, that's just the printout of the different types of FECs there are. Usually the forward error correction methods. Depends on the end device, depends on the switch vendor. I said usually this works out quite well, but because it's in auto mode and it gets auto detected. But if a link is not coming up, it's worthwhile checking on the end device and the switch, maybe just fixing or hard coding the FEC, so that if the auto detection just doesn't work. So let's move up one layer, the network layer. This is about how you configure your switches and make them work together as a network. What to look out for here, if you are using a layer 2 network, that is, you do not have a routing instance in your network, which is true or can be true depending on your design for a monolithic network. then you need to have an IGMP snooping Querier. If you don't have one, your streams will work for 30 seconds and then they will go away. So if you have a layer 2 network and experience the issue that your streams seem fine for 30 seconds and then they go away, you're missing the IGMP Querier. Of course, you can have addressing issues if you just mix up your IP addresses. That's a common networking issue, but can easily be fixed just by looking at the configuration. PTP configuration errors are, yeah, you can have them, especially the domain. Some switches have what they call control plane policing, which is a very good thing, so that your control plane, your switch processor, does not get overwhelmed by packets coming from all over the place, or malicious packets, even so, like in a denial of service attack, so that they police what is going to the switch processor. Some of the default settings cause PTP packets to be dropped if you have a lot of PTP clients, and then you have to adapt your control plane policing. But usually this is outlined in the respective documentation, how you can do this. But if PTP seems to work somehow, but sometimes it doesn't, then that can be down to the control plane policing, just throwing away PTP packets, and then you increase just the amount of bandwidth you reserve for PTP, and then everything's fine. Yeah, we have seen problems with PTP grandmaster failover, so that's at least theoretically it shouldn't happen, but if it happens, it's good to test your system for this. So be sure you have a grandmaster failover test in your test procedures. And also there's a difference if you just like change the priorities of the grandmaster, so that there's a graceful failover, just another grandmaster announcing itself as a new best master, as opposed to just switching off a grandmaster, because then the grandmaster is gone, it has to be detected, and then the network switches over to another grandmaster, and that can behave quite differently. So really make a switch off, or plug the cable, or put down the switchboard, or whatever test that really also tests the detection of a failover, of a grandmaster failure. Yeah, your most common tools for this are your switch user interface and your network management system. I've talked about the IGMP snooping Querier already on the last slide. Yeah, one thing that's important, if you want to build layer 2 networks have some advantages, because they are very easy to configure. There's not much configuration effort, and they're more also the devices can be plugged into any network, but they get messy if they are larger than one switch. So if you have a real network where there's more switches and they are connected, and you have a full layer 2 topology, this can get quite awful. So I would not recommend to do it. If you have a small studio with only one switch and you connect things to it, then layer 2 can just save a lot of configuration time. But you have to look at the IGMP snooping Querier configuration that you need in this case. Yeah, how to detect PTP configuration errors. The first go-to is the PTP counters that you usually have on your switch user interface. The first thing is, are sync packets going out of the switch? That's, just let me see, sync packets here going out of the switch. And if those counters increase, then at least the switch is configured correctly, or at least is sending out packets and is probably configured correctly. What most of the most common problem is that the delay requests do not come in from the end device, and that means that there is a mismatch between the switch and delay request. I would say in 90% the domain is not set correctly, and then yeah, the end device just does not recognize the sync packets and does not see the need to send the delay request packets. But yeah, we have also seen devices where PTP just was not working correctly or something. But usually if you see delay requests coming into the switch and delay responses going out of the switch, then everything should be fine. Good. Moving another layer up into the network control layer. This is about establishing paths inside the network, that is between the switches. And if something is, or you need to look out for, of course, you need, if you have a network controller that does this for you, all the switches need to be reachable by the network controller. Usually it tells you so if it can reach the different devices. Then the most common question is the controller showing the flow routed correctly. So most of the controllers give you a map or something where you can see where each flow is going. We have seen one instance where redundant paths were not disjoint, because and that's something you can check for. And then, of course, you want to check for whether the routes got programmed correctly into the switch. I mean, usually this is not a problem, but if there is a problem, that's something you can check for, that the route or the path displayed by the multicast by the network controller is the same as the path displayed on the switch UI. You can look into the different switches and they will tell you how the multicast goes, which is the ingress port, which is the egress port, and then you just compare it to what is there on the network controller user interface. And again, you have to look at the switch user interface or your network management system and the network controller UI to compare those. And what is also very handy if your switch supports flow monitoring, so that you can really look at if the packet is really using, if packets are really using the path. There is vendors who call that RTP flow monitoring. Other vendors have S-flow implemented. So depending on your vendor, there are different methods to do this. Again, one layer up, we go into the stream control layer. That's where the information from the senders is sent to the receivers, so that they know which streams they should receive. This is done by using SDP files, and usually done using NMOS, as is explained. And again, you have a controller who needs to reach the sources and the destinations to pick up the SDP file from the source and send it to the destination. Are the end devices reachable by the controllers? One other thing is, usually you need to configure your end devices. Most devices are rather flexible in how many senders and receivers they support. And then you need to look at your device configuration, if it's as you intended. But the second thing is also look at the NMOS implementation. It's very easy. You can just use a web browser and browse through the NMOS tree, as was just presented in the last presentation. Then you see if the NMOS implementation or the NMOS representation that is in the end used by the stream controller is the same as your intended device configuration. And sometimes you can have a mismatch there. I mean, that's a bug, but there are bugs in software sometimes. And another thing to look out for is the SDP file, the actual. Is it matching the sender configuration? Again, this usually should be the case, but if it's not, then you might have a problem. And I've seen this happening. And the beauty of SDP files is they're just text files. I mean, you need to know what the different abbreviations mean. but it's human readable in that sense. And there are some NMOS utilities where you can check for devices in the NMOS registry, for example. Again, one layer up is the broadcast control. I mean, we know that. One thing about IP systems, they are stream-based, so there's no embedding because you have separate audios, you have separate video and separate data streams. So you basically need an instance to tie them all together. That's your broadcast controller. I mean, we know it from the SDI systems where we also had the broadcast controller in most cases. And there we create those associations and provide the user with their interfaces, hardware, software panels, whatever. Yeah, I mean, the higher up you come in the stack, the more vendor specific it gets. So there's little you can say about troubleshooting, work with your vendor, look at the logs of the system and so on. That's how you troubleshoot there. An interesting thing is for the broadcast controller is the audio channel configuration. We have heard that there can be in IP world you have streams of audio channels. You can have different numbers of stream channels of mono channels per stream, and you have to decide how you build your system. If you have one stream, one mono channel per stream, this is very resource intensive because you end up with a very high number of streams. You have to have a lot of senders, stream senders, you have to have a lot of stream receivers, and you have a lot of flows inside your network. 8 is the most compatible because it's the lowest level of compatibility in the ST2110-30 standard. And so all devices must understand it. But it's somewhat inflexible because you always have 8 mono channels, and then you can use 16 because it matches what you have in SDI. Some use 4 because it's a compromise between 1 and 8. Oh, there's a mistake, I see. Some also go for flexible. So if I need a stereo signal, I go 2. If I need a mono signal, I use 1. If I have a 5.1 signal, I go for 6 channels and so on. But this can get very complex. So you really need to know what you're doing. For some closing remarks, some general design thoughts, most of those are pretty standard system integrator things and are especially true for 2110 networks, but yeah, they just are true for those as well. Yeah, I mean, they are very powerful and flexible systems, but they are a significant change of the existing technology. It's really a change also in paradigm, and if you're doing it right, they will always also affect your workflows. As any significant technology change, you should adapt also your workflows. Use design decisions to adapt the many possibilities. They're so flexible. If you have to somehow constrain the flexibility again to your workflow, because otherwise it's just too many possibilities for day-to-day operations. This is in the same direction. Don't get carried away by the possibilities. I mean, you can build incredibly complex systems. The question is, do you want that? Or do you want them to be still manageable? Yeah, as I already said, do not mimic your current workflows completely. I mean, of course, you do not want to throw them all away, but look at the technology and what it can do for you, and how you can build more streamlined workflows with a new technology. And be prepared to learn as you go. I mean, you can hear this presentation, you can look into documentation, everything. I once heard a study that 10% of your knowledge you gain from training, 20% of your knowledge you gain from looking at how others did things, and 70% of your knowledge you gain by fixing things yourself. And so be prepared to learn a lot. And start small but relevant. I mean, of course, you do not want to build your complete facility in one go without having tried something out. But if you try something out, make it big enough to be relevant so that you really learn things like have a real network or whatever. Thank you very much.